morning everybody. Welcome to this 5th class of D block and F block elements, and today we will just finish the D block elements, and the next is what we will be discussing about the D block elements are the colors, which is a very important aspects for any D block element. And what we should all know, and we should have some very good idea compared to the other S and P block elements. And in all these cases, starting from the very well known example, what we know that what should be the color of the sodium chloride powder or the potassium chloride powder in the solid state. So, when they are solid, we should have some good idea about these, and we all know that they are white in color. And if I now ask why they are white, so it has no relationship with the corresponding coloration, and if they are colored and if they are differently colored, we know in the visible range we have so many color combinations and so many options we can have. So, in this particular case, the absorption in a particular range is taking place. So, if we have the absorption in the corresponding energy, the electronic energy, what we will see the mostly which changes the corresponding electronic levels of the metal ions or the anions and all. So, if the absorption is taking place in the corresponding UV range and the corresponding color what we see that is white in color. So, there is no absorption in the visible range. So, what we just see that the colors of these compounds, whether they are good metal salts or that ions in solution, and they should be colored in the visible region, because our eyes can detect only those colors where we can have some absorption in the visible range. So, most of these compounds, whether we are getting some ionic compounds, what we will see afterwards for the different metal complexes also, and some of them are the corresponding covalent compounds. So, both ionic and covalent compounds what we can have. So, these can also give rise to the formation of several inorganic materials or inorganic oxide base, sulphide base like these, because all the minerals and ores what we know, they are the good materials to handle. So, if we get those materials in our hand, and if the light is passed to that material, what we see that some part of the electromagnetic radiation will be absorbed. So, what particular wavelengths we are going by? So, material can absorb some parts, say blue region or the green region or the red region of the spectrum, electronic spectrum for the visible range. So, they will be deprived of those wavelengths which are absorbed. So, some part of the electromagnetic radiation is absorbed. So, we will see some other color, that means we will see the corresponding complementary color for the materials. So, this particular absorption not only the visible region, but visible plus UV range. If the absorption is taking place in the visible and the UV range, so what we see that the corresponding absorption and the property we will also see that the absorption energy will be there. So, absorption of a corresponding energy can be there, and if this absorption is taking place in this particular range, so which are due to the changes in the corresponding electronic energy. So, we will be focusing our attention on the changes in the electronic energy, not due to that vibration, the bond vibration or the rotation of the molecule. So, this we are not talking about. So, if there is a change in the electronic energy and this particular thing which is a complementary to that absorbed, some has absorbed. So, what we will get? We will get the corresponding complementary color to that what is absorbed. So, we get the complementary color. So, we should know that what particular wavelength is getting absorbed and what should be the corresponding complementary color in this regard when there is a change in the corresponding electronic energy. So, we call them as electronic spectra. So, in these d block elements we all know that there are 5 d orbitals, and those 5 d orbitals we all know the different 5 d orbitals, and when they are in the free ion state, that means the gaseous state and all, we call they are having the same energy, that means they are degenerate. So, if they are having the identical energy in the gaseous state, but what is forming there, if we go for that particular species say Ni2 plus or iron 3 plus in solution. So, mostly we will be looking at the colors of 2 different types, that colors for the salts and the colors for the corresponding ions if we take those ions in solution. And in some cases also, so some cases also we see that if we have a ferric chloride salt, we know that is a typical salt what we get in the solid state. So, that can be also hydrated. So, the salt, this particular salt will have some color. So, what is happening in the solid state structure is important. So, salt will have some structure. So, in the solid state structure we have Fe3 plus which is surrounded by the different number of corresponding spheres of chloride ions. So, when chloride ions are surrounding Fe3 plus, we should also have some idea that what will be the condition of these 5 degenerate d orbitals or the 5 degenerate d levels. So, in this particular case these are the corresponding ions. So, we have in the solid state we have the ions which are available to surround the central metal ion in the corresponding crystal lattice. So, we have the crystal lattice and the lattice is surrounding all these. So, if there is some effect and there is something which can part up the d orbitals in terms of the corresponding energy and the geometry of this particular solid state structure, we will see that these will not be d orbitals no longer, they are degenerate no longer. So, these 5 orbitals may not be degenerate. So, they can be separated into 2 groups. Say the 2 groups are in one particular group it is 2 orbital and another it is 3 orbitals. So, that we will again discuss in detail when we will study the coordination compounds. So, this solid state thing will be that no, these d orbitals will not be degenerate in nature, and if we get these 2 levels, there can be some transition, electronic transition like this in the electronic spectra. If we have some unpaired electron in these d orbitals, we know the very basic definition of these d elements or the d block elements or the transition elements in the first series, say they are having multiple number of d electrons in the different d levels. So, they are having the general configuration, electronic configuration is 3dn. So, these different number of electrons, if they are occupying the ground state, so energy will be absorbed in this particular range in the visible or the UV range, and the electron can be promoted from the ground state to the excited state, because already we have created, due to this particular splitting of d orbitals, we have created 2 levels. So, the energetic transition can take place, which is equivalent to, we all know, that is delta E, the separation which is equal to h nu. So, to how to correlate this nu we all know the nu can be correlated with that of our lambda. So, depending upon the energy separation between these two levels, we get the corresponding nu value, the frequency for the transition as well as the lambda value for that. And what we see that since the absorption is taking place, so this absorption is there. So, we get the corresponding complementary colors from the with the spectrum, the complete spectrum for the UV to visible region, some part is getting absorbed and we get the corresponding complementary color. So, what about these in solution? So, in solution also when we dissolve a particular metal salt say in water. So, if these are all water molecules surrounding the ferric ion center in solution. So, what we see there that like that of our anion surrounding the central metal ion, the water molecules we all know that these water molecules since iron is in the tripositive charge. So, water molecules all we know that it has 2 lone pair of electrons for this structure of HOH. So, these lone pair of electrons will be donated and they are having some charge separation which is delta minus and delta minus with that delta plus and delta plus. So, charge separation can take place and we generate some dipole. So, dipole will be all directed towards the central metal ion center, and as a result again like that of our interaction what we have seen in the solid state that again the degeneracy of the d orbitals will be lifted. That means, they are no longer degenerate and there will be 2 groups of d orbitals of different energy. So, we just what we have seen that we have the 2 groups basically, and between these 2 groups there will be that particular transition. So, this interaction is typically one such thing where the absorption can take place. So, this particular color when how many of them, that means how many of these water molecules are there, we all know that when the ferric chloride or any other ferric salt is dissolved in water, the species what is forming in water is FeOH2 whole 6 3 plus. So, 6 of them surrounding in a regular geometry which is octahedral in nature. So, that octahedral structure surrounding this Fe3 plus in a specific way it can split these d orbitals. So, this particular color, that means the color between these 2 levels. So, the color between these 2 levels also depends on the number, this number is important, that means these are 6, depends on the number and also the shape of the complex. So, the very basic or very simple thing what we can understand from there is that if we know that when we dissolve a particular metal salt, so we have a metal ion salt. Okay, so, there are these things. So, you have metal ion and the salt is for the corresponding anion. Suppose you have the nickel chloride, you have the ferric chloride and so on. So, this particular metal salt, so it is in that particular salt we all know that most of them can be separated in the solid state. So, the solid state color we always can have and the nature of the corresponding groups which is surrounding this particular species. So, if you change for the corresponding hexaaconical species which is again octahedral like that of our ferric one. So, again 6 water molecules will surrounding the nickel center and we all know the corresponding color which is a very characteristic one whenever we have nickel and if it is surrounded by water like ligands. So, these are good ligands. So, 6 ligands are there. So, we get something which is the very basic foundation of the coordination compounds which is the corresponding Ml6 cation, since water molecules are all neutral. So, the overall charge on the complex is Ml6 2 plus, but what should be the color? Already we defined that the depending upon the nature of this ligand and the number of this ligand and the geometry and shape of the complex, you have a particular color. So, if we move from this ligand to some other ligands, suppose this is L1, if we move L1 to L2 to L3, what happens therefore? That if this is there, and we all know that if these are octahedral, so there is some separation which is our delta E. So, depending upon the nature of these ligands, so therefore, the color depends on the nature, number and the shape of these ligands. So, this delta E basically for this first ligand, this will be delta E1, for the second definitely it will change, whether it can go up or it can go down, the color will change accordingly, but you have a separation of delta E2. Similarly, if we go for the third ligand, you can have a separation of delta E3. So, always we should know the trend basically depending upon this energy gap from delta E1 to delta E2 to delta E3, we can have the corresponding variation in all these colors as we move from one ligand to the other to the third one. So, that these can be correlated definitely to the corresponding lambda values. So, this will give you the lambda 1, this will give you the lambda 2 and this will also give you the lambda 3, and obviously, the colors will change. So, the solution colors will be changing. So, what we see here is that how we go for the development of colored ions. So, if we have the ions, so when ions are there in solution, so they will give rise to some coloration which is different from that of your S block and P block elements. That means, if we have sodium chloride in solution, we cannot see any color, but if we have the corresponding nickel chloride or copper chloride in solution, we have the corresponding color. So, as we define the transition metal ion compounds or the complexes are often colored because of transition between the d orbitals of different energies. So, some of them will be in the lower energy which are in the ground state, and some will be in the excited state which are of the first excited level or in the excited level. So, when an electron moves from the lower d level to the higher d level, the energy of excitation corresponding to the frequency of the light absorbed, and as a result, if we move for all these metal ions, say tetravalent vanadium to copper, we can see very characteristic color. It is taken again from your CBSE book. So, if we clearly see this change in the color, and once you very much accustomed to the change of these color, you always suspect, because there is a difference in these two blue colors also, there is a difference between these two green colors also, then this pink and the light pink color and the yellow coloration. So, depending upon these 7 colors, you can immediately say which one having Ni2 plus. So, as we have discussed right now, that if you have a nickel salt, nickel chloride or nickel sulphate or nickel nitrate in your hand and you dissolve it in water, only due to the presence of different amount of anions, some changes, little bit changes of these species, this color will take place. Otherwise, you have the typical Ni2 plus color, which is very much that of this one. So, this is one way of identifying a nickel salt in solution. So, any unknown solution, if it has a color, what you can do is a very simple analytical experiment always we do. You use some reagent. So, this particular reagent can react with this nickel, because if this solution which is a little bit concentrated, definitely it is in the decimolar concentration, but if you go down this concentration, the color will be fading away and we get more and more faint color. And sometimes it is very difficult by your own eyes, that your naked eyes, we take the help of the corresponding colorimeter or spectrophotometer to identify that particular color. But if we get that, we will again discuss in detail when we study the coordination compounds, that if this is there, that means the nickel center is surrounded by 6 water molecules which give rise to a particular coloration to the medium. Now, if we give you some characteristic species or other species like say ammonia, so ammonia will change this color, and sometimes we can use something which is also known as some reagent which can separate out this nickel as some insoluble material or insoluble compound which is not soluble in water, which is separating out. So, that is another way of identifying this nickel by using that particular reagent which can give you the precipitate, like identification of chloride by adding a solution of silver nitrate which gives you the precipitation of silver chloride. Similarly, if we add here, we all know that the DMG, dimethyl glyoxime in ammoniacal medium, if it is added to this nickel salt, this will give rise to the corresponding precipitation of a very well defined colored species which is insoluble in water. Okay. So, when this particular part, that means what we are discussing just now, when a particular part is absorbed, we always see a complementary color of that light what is being absorbed. So, this is corresponding very well known colored wheel. We all know that if we have a typical solution, that is a solution is red, blue and yellow, and also we should know that is when we just simply draw the color of the different paints or the colors. But what we see that the solution color, why the paint is colored to you, why the paint is yellow, it has some characteristic color that we will again discuss as some inorganic compound which has a very bright yellow color. And if there is some other compound, if it may not be an organic compound, it can be organic dye also. Similarly, some is also blue, which is also may not be inorganic, that means metal ions are not there, only organic part is also colored. So, this is the wheel which tells you the corresponding mixing procedure, that we know that in VIBGYOR we have 7 colors, but we have 3 basic colors, and the mixing of those colors we ultimately get, when all of them are mixed together we get white color, but if these 3 are mixing we get a black coloration with some other colors which are derived from the mixing of direct these colors. So, if we get 3 plus 3 6 colors in that way, then because we have electromagnetic spectrum starting from your violet to red, which is your VIBGYOR. So, VIBGYOR as we move, so this particular coloration, it is basically some amount of practice and not a memorization, but you can have some practice that okay, we have the red, blue and the green thing also, and we have also the corresponding magenta, yellow and cyan color, and how the color is moving from, say as we move from violet range to the red range in the electromagnetic spectrum. We know that the corresponding rainbow, that the color how it is spreading, how it is nicely spreading when the prism is given to the white light, it is basically spreading, but sometimes we are unable to detect a particular light by knowing these 2 colors, but in between we should have some good idea which is light blue and which is towards red, which is violet in color, similarly which is rose red and all these. And some is also, if we mix little bit of blue to that, we get the cyan, and what the mixing proportionate is different, that means the mixing of cyan and green will give you something which is also a different color, that means color is fading away. So, what I was telling you just now, that if you have a very good or a different type of green coloration for the nickel 2 plus in solution, and when you dilute it out, it gives you something, some dilute solution or the dilute or very faint green coloration, and ultimately it goes for the corresponding coloration, and which is very difficult to detect sometime as the origin is typically a green in color. So, as some part is absorbing, so wavelength range, if you just simply use the corresponding colorimeter or spectrophotometer, what we see that a particular range of wavelength can be divided, they are not of equal, separation is not of equal size. So, it is 400 to 424, so is only 24 nanometer in length, but this one is the smallest one, you see that the 570 to 585 only 15 nanometer long. So, when violet is absorbed, we see the color of the solution is like this, which is green yellow or the greenish yellow in color. Similarly, when some part is absorbing, so when all these, so this has been categorized like violet, blue, green, yellow, orange, red, and these are the corresponding complementary colors, and as we move there we get the corresponding color due to the complementary color. So, when we see some solution, we always see what particular color is absorbing, because quantitatively we will be just recording, if you want to record the corresponding absorption in these values only. That means, when a solution is typically blue such as copper or nickel in presence of ammonia, definitely your lambda max, the wavelength which is giving you the corresponding maximum range of this particular wavelength absorption. So, in the electronic spectrum, the spectrum what we get, that is in the range of 570 to 585 or sometimes 560 nanometer only. So, the blue solution will definitely give an absorption in this particular range. Similarly, yellow will give you in this particular range, and the blue and cyan blue will also give you these colors in a different one. So, if we just now go back what we are just discussing, that what is you are having these compounds where the colors of the different salts, what we are just discussing about the corresponding salts like nickel chloride or iron chloride. So, some idea we must have about the corresponding colors. So, here we have taken say 5 plus 5 8 salts. So, these are not solution color, what your book is discussing in your book it is there, but whether we are able to identify those solutions from these salts. So, when you dissolve these salts, and these salts we know that if it is nickel sulphate, nickel is in bivalent state. Similarly, if it is copper, copper is in +2 state, and if it is iron, iron is in +3 state or +2 state. So, depending upon the oxidation state you have different number of unpaired electrons and the colors will all be different there. So, among these 6 colored species we have 2, 3 very well known or very well defined white color or the colorless species or the white powder. Basically, when you dissolve it in water like sodium chloride, it will not impart any color to the solution and it has a very faint coloration. So, from left to right as we move for the 3D elements from left to right from scandium, this is definitely a scandium 3 oxide. So, which is Sc2O3. So, scandium oxide is definitely a white powdered compound. If we try to get that compound also during some identification or isolation process, that scandium oxide what is going out from the medium as precipitating out from the medium like zinc oxide would be white in color. Similarly, the titanium. So, titanium is in +4 oxidation state which is TiO2, we all know is a very useful ingredient for white paint. So, titanium oxide is typically white in color, but vanadium is vanadium 4 plus. So, vanadium is in 4 plus oxidation state. So, which is basically VO2 plus. So, VO2 plus is there and which has a typical coloration. So, vanadium sulphate when you dissolve, this gives rise to a particular type of coloration. So, this also gives us some idea that what is vanadium sulphate. Your vanadium sulphate is VOSO4. So, the species what we get is the V bound to O having a charge of 2 plus. So, we get basically VO2 plus species which is the vanadium ion. So, vanadium ion will have has a particular color, we know if we just dissolve, if we know the salt color also. Similarly, the other species also we can find out that corresponding species is there. So, this species like VO2 plus which is vanadium 5 species, and then VO4 3 minus which is also another vanadium 5 species and which are having a very pale yellow coloration. So, knowing these ionic coloration for these ions, we can find out which one having this particular vanadium ion or the corresponding VO2 plus species is present. So, this particular one. So, next one is definitely a chromium salt, but the chromium of different salt which is sodium chromate Na2CrO4, and which we all know is a very bright yellow. It has been used as a paint also, so it can be used as a yellow paint to us. So, sodium and chromium, you see that the chromium in the highest possible oxidation state, that means chromium in 6 plus. So, you do not have any electron in the chromium d orbital. So, it is a D0 system, but still due to charge transfer transition it is highly colored. So, oxide ions is basically responsible for charge transfer to the chromium center which is devoid of any d electron. Then manganese 2 chloride having unpaired electron still there in the d level, but which is faint pink in color. So, solution color is very faintly colored. So, sometimes it is very difficult to identify through our eyes. Then this particular salt is not a typical salt of iron, that means ferrous chloride or ferric chloride, but we should also know that this is ferric one. So, it is potassium ferricyanide. So, presence of other anions in the solid state as well as in solution can change the corresponding color of the species like that of our potassium permanganate. So, potassium permanganate is changing its color due to the corresponding charge transfer condition. So, the promotion of this from the oxide level to the manganese level giving this color. Similarly, here also the ferric ion, the electrons are there, then the cyanides are there, so it has a different color. Then cobalt 2 chloride is a very standard salt, cobalt in COCl2 hexahydrate dot 6 H2O, which has a nickel 2 is also there, nickel 2 nitrate is green in color. Then copper 2 sulphate, we all know the copper 2 pentose hydrate is has a very characteristic color, we all know this. So, as we move, as we go here, copper 2 plus is a 3D9 system. So, the next one will definitely will going back to like that of colorless species, which is the zinc salt. So, the zinc 2 sulphate heptahydrate ZnSO4 7H2O is also colorless. So, this gives us some idea what are the salts and how these salts we can identify. So, let us take some example of these, that the complex ion species what is forming in the solution and which is important for all these cases apart from the corresponding aqueous thing, that means the nickel is in the solid state. So, which is green and a characteristic green type of color. So, when you dissolve it in water medium, it gives you the corresponding aquated complex, that means the hexa-aquo nickel 2 plus. So, this hexa-aquo nickel 2 plus is green in color, as we all know, compared to your copper which is blue, compared to our cobalt 2 plus which is pink in color. So, when we dissolve it, we see due to the presence of the different ligands, we told you that if you have the different ligands present over there, you see so much change in the coloration due to the presence of this nickel only. So, the identification of nickel by all 4 ligands what I am just discussing to you, L1, L2, L3 and L4, or if this is L1 then L2 and L3 and this is L4. So, these basically give you all these colors, and if you are able to these colors simply in the test tube, you should be able to detect that whether you have the nickel in your hand. So, this the last one basically, when you dissolve any nickel salts and nickel chloride, you will get the hexa-aquo nickel species, and when you just simply add ammonia to that, all the water molecules one after another can be replaced by ammonia molecules. So, the nickel environment is changing from NiO6 coordination sphere to a NiN6 coordination sphere, and the further change in all these things, that means from the ammonia to ethylene diamine. En is nothing but the ethylene diamine, which is the typical organic ligand, bidentate chelating ligand that I will discuss in detail afterwards. But if we just simply go back to here, which is having a different geometry, and that is why the color is also different. So, shape is different, color is different, and the corresponding anion here now like that of our solid state structure, where we are discussing that nickel chloride in the solid state also surrounded by chloride ions, but here also in the solution when you put more and more chloride concentration, you can add simply dilute hydrochloric acid 1:1 hydrochloric acid, or simply any other saturated solution of sodium chloride or potassium chloride, it gives you the tetrachloronickelate salt. That gives us some idea how the corresponding K2NiCl4 is forming in solution and what should be its color. So, you see the color is completely different to that of your corresponding aqueous species. So, depending upon this corresponding color, what we have seen just now, that the yellow color we have seen that is the chromium compound of particular type. So, if we take the example of 2 of these compounds, and we do not know what are these, but if you carefully watch or carefully notice the corresponding color of these powder compound, that one is very bright yellow and another is very crystalline also, the red crystalline thing like our sugar. So, this is a very good red crystalline compound, but these are of some say the grain sizes are there. So, both of them are of chromium compound. So, these chromium compounds, this is chromate and this is dichromate. So, there is again a change that we will see afterwards also, but these two are very useful species when we will talk about the chromates and dichromates for the corresponding formation of these chromates and dichromates from some minerals, say chromite ore, because from the chromite ore we can separate out these two species for the corresponding preparation of the corresponding sodium dichromate, which is Na2CrO4, and the potassium dichromate, which is K2Cr2O7. But this particular color which we can see, because this lead chromate, which is if it is sodium chromate, this is sodium chromate, we can prepare lead chromate also by addition of lead nitrate or lead chloride to a solution of this sodium chromate, we get the corresponding precipitation of this lead chromate. but this is a particular mineral which is known as crocite. So, crocite is the mineral ore which is found in South America. So, in the South America, in the desert part, which basically get that thing. But if we in the laboratory, if we make the lead chromate, which is differently colored, because this can be used as a very good paint which is known as chrome yellow. So, industrially it is well known. So, chrome yellow paint, we paint the automobiles, we paint the school buses like this with this yellow color, because yellow color is very much visible from a distance. But this particular lead chromate which occur naturally, having a spectacular red long crystals, you see this color is completely different compared to our lead chromate what we can make in the laboratory. Why this is so? Because this is typical crystals, and these are from the earth, and the corresponding hydrothermal vein it is forming, and depending upon the nature of the corresponding crystal type. So, crystal type is basically changing its color. So, the dense packing of this crystal and the nature of the crystal also, the crystal system will give you a completely different color from this yellow to red, and this is a very well known thing and is a very good colored thing. So, if we can naturally get this particular compound, and if we grind it like that of our dichromate, we can use this also as a red pigment, and this yellow color can be utilized for the painting, the corresponding chrome yellow painting to the school buses. Okay. So, what we see therefore that this will go later on. So, this F block, before going to the F block elements, what we see that this chromate and dichromate thing what we are discussing right now, that how you get the dichromate, that means it has a chromium Cr2 species is there, 2 from a chromate which is a chromium 1. So, 1 chromium only. So, which is all we know that CrO4 2 minus is the chromate ion, and if we go to dichromate, so chromate to dichromate we can move. So, Cr to O7 2 minus. So, is a dimeric product of this, where you have a chromium chromium thing, and there is no such chromium chromium bond, but you can have a chromium oxygen chromium link over there. And interestingly, this is related to the ore which is also having the name of chromium, so which is chromite. So, chromite ore can be handled, which is a ore containing Fe, iron is there, Cr2O4. It has a characteristic color also, and we can use this particular ore. And if some unknown practical class or some analytical chemistry class, which we find are that how to identify that whether you have chromium in the that chromite ore, that we will see that some fusion reactions, that how you can fuse it. That means, if you go for some fusion reaction. So, fusion reaction is that heating this with some other powder such that you get a melt. So, once the melt is available, so melt, if you go for the corresponding fusion with some sodium or potassium salt, we all know that this particular sodium or potassium salts are very useful for the solubility in the water. So, if the melt is forming which is soluble in water, that means something we are using for this particular fusion, and sometimes during the fusion we require that this is the powder. So, chromate ore is taking in the powder form and is mixed nicely with another powder. So, another powder which one also giving the melt. So, it gives us some pores. So, some gaseous product should come out. So, some carbonate salt is very simple, is that the sodium carbonate you use. So, sodium carbonate you use with more oxygen from air. So, we pass air, or you can do in the air also, and this particular fusion is taking place at a very high temperature, say above 1000 degrees centigrade, in the range of 1000 to 1300 degrees centigrade. So, in the laboratory also we can take a mica foil also, and mica foil, if you just sandwich between two mica foil this mixture of these, that means the chromite ore, the sodium carbonate and air is always present in the environment. If you fuse it with that on the Bunsen burner, we get the melt. So, melt is forming. So, once we heat that particular one, so this one will be converting to something which is present in the melt. That melt, what is there is that we take out this as the CrO4 2 minus, and in presence of the sodium also, and during this fusion what is going out as the gaseous product is always definitely we are heating a carbonate salt. So, carbon dioxide will go out and it makes some holes over that particular melt. So, melt will be a very fluffy material. So, this basically give rise to the formation of Na2CrO4 chromate is forming along with some amount of that Fe2O3. So, iron will not give you some kind of ferrate there, only that ferric oxide is forming with the elimination of this carbon dioxide. So, if we use the mole ratio of 4 with that of our 8 of Na2CO3 and 7 of O2, we get 8 of this, twice of this, and 8 of CO2 will go out. So, this melt is there. So, melt is forming at a higher temperature. So, when we just simply allow it to reach the room temperature, when we allow it to reach to the room temperature, the solid what we get after cooling. So, what we do is the cooling and we get a solid product. So, solid product what we will have both. So, this is the thing that where we can separate the solid. Only thing that if you pour some water, so water we add, and since it is a sodium salt, this will be highly soluble in water, but this is the oxide which is insoluble in water. So, that gives rise to the separation process, that means one will be soluble and another will be not soluble. So, Fe2O3 will be there as residue. So, this Fe2O3 will be there as residue and Na2CrO4 is there. So, Na2CrO4 will be there in the filtrate. Now, how to get this one, because ultimately we also can be able to make this. So, once we make sodium chromate, we just now I told you that you add Pb2 plus to get chrome yellow, the lead chromate. The chrome yellow is forming, which can be used for painting. So, once you use this, so just simple acidification, because most of these oxides, because this is also a typical oxide which is coming from this your oxide mineral like this chromite. So, most of these things in presence of acid H plus. So, once you get this the corresponding acid, so sulfuric acid we basically try. So, once you add sulfuric acid, this can be giving rise to something that the sodium will be taken out as the sodium sulphate from there, and this will be giving rise initially the chromic acid, and that chromic acid will be condensed together. That means, when we have some of these, because this chromate is Cr, we all know that chromate is having this, this and this, and when this particular one is getting protonated by H plus of this addition. So, when you add this H plus, this will be protonated. So, two such these species, that means one OH on the left and another OH species containing species on the right. So, what we get there? So, two such species can condense together. So, if we get from there, which is H2CrO4, which is the chromic acid, which can also be prepared. We all know that the chromium trioxide is a well known oxide, which is the acidic oxide. When it dissolved with water, we get H2CrO4, which is again the chromic acid, which has a very good cleaning property of organic material or the organic greases. So, glasswares which is sticked with some very sticky organic material can be cleaned by this, because the chromium in higher oxidation state can be utilized for oxidizing those organic compounds. So, this can also be used in the leather industry for tanning, and all this chromium has some useful use for all these purposes. So, now you see that if you get that chromium attached to OH on the left and chromium attached to HO on the right, and if we consider two of them, so similarly this is there and this is another O, and this is O and this is O, and this is O and this is O. So, what happens this next type? So, next step is that we can have this, that means we get the removal of water molecule. So, this water molecule can be removed from there as H2O, and we are ending with this link, that means chromium oxygen chromium link is established in the dichromate species. But is that you cannot have, you have the possibility for this also, but it is not that only one end of this chromium and another end of this chromium. So, this is tetrahedral in structure, this is also a tetrahedral in structure. These two are coming to each other and they fuse together. So, fusion can take place only through these two species only, that means this one. So, these other three parts are away from this link, that is why this is forming, but chromium O chromium and chromium O chromium is not forming. So, this definitely is not forming over there, because the other end is not close to each other for this condensation reaction. So, once we get there, that means this is forming over there as sodium corresponding one as the sulfuric acid is added. So, you have the sodium chromate. So, Na2Cr2O7 is forming and this sulphate is going as the sodium sulphate Na2SO4, and both of them are in solution. So, in solution what we get, that then a large number of water molecules are there also forming from there, and we go from there the corresponding evaporation. So, evaporation technique from there basically give rise to the corresponding crystals of the sodium as dihydrate. So, sodium dichromate can be separated out from here as the dihydrate, because we know that during this particular process you have the corresponding solubility difference. So, first the sodium crystal which are having sodium sulphate crystals which have higher solubility, that can be in solution, only the sodium chromate can be separated out, this will be in solution because it has a higher solubility. So, the solubility difference will help us for the separation of sodium sulphate from sodium dichromate. So, this we basically use for different purposes, because this dichromate is very useful for making potassium dichromate what we use. So, Na2Cr2O7 what we get from the chromite ore, we can make from there the corresponding potassium salt K2Cr2O7 by the addition of, these are basically red crystals. So, this particular one by the addition of hot and concentrated solution of potassium chloride. Then again this is forming and the potassium chloride is giving you the potassium to get the corresponding salt, as well as some amount of sodium chloride will be forming over there. Then the separation again we follow this particular one, that what are the thing, that means what is crystallized from there. So, depending upon the solubility differences between this potassium dichromate and sodium dichromate. So, sodium chloride will first crystallize and then the potassium dichromate, which is formed by using that particular technique, the separation we basically go for fractional crystallization. So, we are going in fractionation, the corresponding crystallization process for these two. So, this is one example what we know, that these are the corresponding hexavalent chromium present in this chromate and dichromate, which is very much similar to that of our hexavalent sulfur behavior. So, hexavalent chromium can be very much useful for using this as the corresponding primary standard in volumetric analysis. So, it can be a primary standard solution in volumetric analysis. What we can do in acid medium. So, we have little bit strong acidic condition. So, this acidic condition is maintained such that we are handling something which is only Cr2O7, that means the dichromate ion, because the formation of this dichromate to chromium 3 plus will give us some idea about the corresponding reduction process, which is for these 2. So, is 2. So, hexavalent to the trivalent. So, is a 6 electron transfer process, and which is only achieved having some corresponding E0 value of 1.33 volt, which is only achieved in acidic medium. So, that acidic medium is very much useful, and we can get the corresponding one. So, 1.33 volt for this volumetric analysis to get back to the chromium as chromium 3 plus, and in presence of say this on the left hand side we put for the balance purpose 14 H plus and giving rise to the 6 electron transfer forming 7 H2O definitely. So, 7 of these dichromate things are going out. So, these are forming your water molecules. So, this has a very good primary standard solution. So, we can use it as because it is temperature, because it is a crystalline form, that whatever potassium dichromate we make which is highly crystalline, which is non-hygroscopic, it cannot absorb water if you keep it for a longer period. And this highly crystalline and the purity is also very high, it is not decomposing with time with air and oxygen in the of the air. So, what we get over there, that this can be utilized for any oxidation reaction or the redox titration. So, if your unknown solution contains Fe2 plus, so Fe2 plus we can take in the conical flux and we can titrate it with dichromate, and this dichromate in this burette. So, we have this in the burette and we get the corresponding titration. So, which is thing is that the dichromate is there having some known concentration. So, this dichromate is having some known concentration, say n by 10 dichromate solution. So, n by 10 dichromate solution we can use to identify the corresponding unknown solution of iron. So, this iron, so the corresponding titration between Fe2 plus and Cr2O7 we should know, and how we can detect the endpoint, that is also a challenge. So, we should know what is the indicator, say particular indicator we call this as the redox indicator. So, barium diphenyl amine sulfonate is used, which at the last drop of dichromate solution can changes this color when all the iron is exhausted, and that can be indicated by the corresponding exhaustion of the iron solution from the medium. So, by knowing the concentration of the standard solution, standard primary solution for the volumetric analysis of iron, we can identify the unknown concentration of any iron sample. So, it can be any iron ore, it can be any iron material or any other species having iron species in there. So, not only iron, because since we are utilizing the oxidizing agent, the dichromate as the oxidizing agent for oxidation. So, the other species also, this iodide can be oxidized. Similarly, we can oxidize stannous ion Sn2 plus by using dichromate, then H2S we can use, and obviously this Fe2 plus we know that this Fe2 plus can be converted to Fe3 plus. So, all these reactions, that means the reactions with dichromate we should all know, this is there in your textbook and you can learn also nicely for this. But the only thing is that what is the type of reaction it is taking place over there, whether this iodide is only oxidizing to iodine or not. So, that is the oxidizing ability, how strong your oxidizing agent is, because the E0 is known to us. This E0 is important. So, this 1.33 volt is important. So, how strong that is to convert iodide ions to the free iodine, because iodine is liberated, and sometimes if it is saturated one, the solid iodine crystals are seen floating over the solution what we are titrating. So, this is there, but whether this particular thing can oxidize further, that means addition of oxygen simply, that means ultimately we know that this can be oxidized to iodate ion like chlorate, perchlorate, etc. So, it can also be oxidized by iodate. So, we should know the corresponding product and the number of electron transfer reactions. Similarly, for Sn2 plus we should know that it is definitely going to the stannic state, that means if this 4 plus state. Similarly, the reduction of H2S, and we should also side by side know another sulfur bearing compound is S2O32 minus, which is the anion of thiosulfate. So, anion of thiosulfate, if we know that anion of thiosulfate how it works on this particular dichromate. So, dichromate how it is reacting with this and how it is reacting with H2S. So, that will give you the corresponding liberation of sulfur in the elemental form, that means sulfur as 0. So, this is all about your chromate and dichromate thing. So, simultaneously or the parallelly we can have the two other compounds which are very important, analytically also important. Those are like dichromate, those are permanganate and manganate. And there also we will see that this permanganate and manganate we can have the ore like that of our chromite ore. In this particular case it is the pyrolusite, and this pyrolusite can be fused not by our sodium carbonate what we have used in the previous case to get the melt. Again the melt, this is the particular process also for identification for both, that means the chromium and manganese. These are the special test or the fusion test or the formation of the melt to get the corresponding species which can be identified very nicely. So, here also we can use a mixture of KOH or NOH or KNO3, simply the KONO3, which both you can go for the corresponding supply of potassium ion, because the cations we have to supply the potassium ion, the sodium ion, and also some amount of oxygen, and in this case the fusion process is little bit faster. So, fusion with potassium nitrate is faster. So, melt is forming there like that of our chromate, which is giving rise here also the manganate, which is the green melt. So, we get the green melt. So, we add water, cold water is added and little alkali we add, and that particular little alkali is basically because this particular thing is stable in alkaline medium. So, we get a, so it is green melt. So, we get a green solution. So, from this green solution we go for evaporation. So, this evaporation is basically if we use potassium it will give you K2MnO4. So, that K2MnO4 is the green solution which can go for the reaction with water forming permanganate as well as manganese dioxide. So, this can be converted or electrochemically this can be oxidized. So, this simple direct reaction of this with water molecules. So, 3 of these can react with 2 of these water molecules to give us the corresponding species as twice KMnO4 plus MnO2. So, some part of the manganese is lost as again back of this MnO2, that means dark brown MnO2 compound plus 4 KOH. So, this KMnO4 definitely like that of our titration process, that means the permanganometry we can do with this KMnO4 solution, but this can change concentration with time and which is also not very pure. So, it is not a primary standard solution, this is a secondary standard solution, and which can again be made. So, you can take this in burette and unknown iron 2 plus in solution. So, not only iron 2 plus, many other things, because this since it is a secondary standard solution it can be standardized with oxalic acid, which is a primary standard by knowing some amount of oxalic acid in a solution of say in the strength of n by 10. So, either sodium oxalate or oxalic acid we can make, and that can be used to standardize this solution, and ultimately iron in the conical flask can be titrated with a corresponding just standardized solution of KMnO4 by oxalic acid for conversion of this Fe2 plus to Fe3 plus to know the corresponding unknown concentration of iron in the medium. So, any other reducing species, we can utilize for this, and this particular case, that means when we use the potassium permanganate and potassium permanganate titration in acidic medium, that means H plus, its E0 value is plus 1.52 volt. But in all other cases the number of electron transfer is different. In faintly alkaline medium, which is giving rise to the formation of this both, that means the MnO2 and this KOH like that. So, the permanganate can directly give you MnO2 in the faintly alkaline or the neutral medium, but your E0 values are different. So, this can also be oxidized for some important species like nitrite. We all know that the nitrite is a very important species to study. So, this nitrite can be oxidized to nitrate in presence of water, again water and this water. So, nitrate. So, any unknown concentration of nitrite can be titrated for this using this potassium permanganate to convert it to nitrate. So, this is a typical example. Instead of this estimation of iron, you can analyze the unknown nitrite concentration also in solution by permanganometry. Okay, thank you very much.